Hello everyone, this is Team 2 and we will be presenting our project Data-Driven Prediction of Building Energy Consumption using occupancy and environmental factors. The complexity of acquiring occupant-related data has limited its use in energy predictions. Previous research mainly focused on predicting energy consumption by relying on outdoor-indoor conditions, envelope details, etc. This study aims to provide a machine learning approach to predict energy consumption for an office building in Berkeley, California, considering the occupancy count and indoor and outdoor conditions. The motivation to tackle this problem was inspired by the fact that more than two-thirds of the world's population will be living in urban regions by 2050, according to the UN. Also, building industry contributed to 37% of the world's CO2 emissions and 36% of the world's energy usage in 2020. Building energy models can be used to optimize and assess several design options to enhance building energy efficiency. With the widespread of sensing technologies and IoT, along with the increased accessibility to building operational data, the use of data-driven building energy models is now possible. And those are the main categories used in the literature for energy prediction.
So we have one main objective, which is to predict the total energy consumption using the meteorological, indoor environment, occupancy-related, and building operation data. In order to achieve that, we first have to identify the correlations between the different physical attributes and the total energy consumption. And due to the limited occupancy data points, we will imputate the occupancy missing data using different machine learning models based on the Wi-Fi connections. The datasets for our different attributes range from 2018 to 2020. The temperature set points, filter supply airflow rate, and the supply air temperature datasets had many missing data points, which would be imputed in our future work. After flattening the different datasets in a data warehouse, we ended up with 11K data points.
The first thing we did after merging the data is to take a look at the Pearson correlation to check the relation between the attributes and decide which attributes to use for every objective. The final correlation matrix is as shown. Once we decided on the independent variables, we visualized the shape of the final attributes as shown. Each group represents the range of the values on the x-axis and the count on the y-axis. Finally, a prediction roadmap is presented that collected all the attributes used in the prediction and what they are going to predict or imputate. We used the Wi-Fi connection to imputate the occupancy for the missing values. We also used the time and the weather conditions to imputate the set point temperature. Once we did those, we added the HVAC rooftop units data to the aforementioned attributes to predict the total energy consumption.
Since we have only 3 months data for occupancy, in order to impute the occupancy, we use Wi-Fi connections as a predictor because they have high correlation. At first, stationary devices have been removed from the Wi-Fi connections. Then 2 floor Wi-Fi connections combined and total occupancy have been considered to avoid the collinearity among the Wi-Fi data for the 2 floors. dbScan clustering has been employed to clean the data from outliers and noises. Based on the previous studies, 3 different machine learning models, which are linear regression, decision tree regression, and artificial neural network regression, have been used to predict occupancy based on Wi-Fi connections. The results showed that the decision tree regression outperformed over the 2 other models in regards to the value of R-square and root mean square error.
Regarding the temperature set points, we are trying to imputate all the missing data using different machine learning models. But first, we flattened the date attribute to month, day, and hour in order to use machine learning models that doesn't deal with time series. So we created several models such as SRAMA, ARAMA, Poisson regression, SVR, MLR. But the results were not promising. We got negative R-squared values for all the machine learning models except for the multiple linear regression, and we calculated the root mean square error for all of them as well. This is an ongoing process, and we are still trying different machine learning models to imputate the missing data.
According to the reviewed literature, the commonly used machine learning models for building energy consumption prediction have been identified. These models were then tested using the clean data set. The preliminary results show that the random forest regression model outperforms the rest with an R-square of 0.836 and a root mean square error of 4.54. Next steps to be considered in this project is the further investigation of attributes affecting the set point temperature, since the external weather parameters yield unsatisfactory results. Using a larger data set with the predicted occupancy and imputed data in the energy prediction model, cross-validation and further evaluation of the models will be conducted to identify potential weaknesses, the most influential attributes, and to avoid overfitting. And finally, exploring other accuracy and error metrics and visualizing the error distribution of the prediction models. Thank you for listening.